Another example, problem 10, chapter 1. In this problem, we have Jupiter, Sun, and also a particle in the Jupiter's orbit. And the question is, what should be theta, the angle between the line between the Sun and that particle, and the connecting line between the Sun and Jupiter, that theta. What should be this theta in which that this particle experience the same gravitational force from both Sun and Jupiter? So the gravitational force toward Jupiter must be equal to gravitational force toward Sun. To make it more clear, let me draw that figure again. This is Sun, this is Jupiter, and this is the orbit of the Jupiter. And we have a particle here, and we want to find this angle, theta. So the problem says this force must be equal to this force, gravitational force from Jupiter and gravitational force from Sun. And you can find all the numbers that you need to solve this problem from table D2 in appendix D of your book. And these two forces, if I call the mass of the Sun ms, mass of Jupiter with mg, and the distance between them, if I call it r, the distance between this particle and Jupiter, if I call it, let's say, x, then the force between these two is going to be g times mass of the particle times mass of Jupiter divided by the distance between them squared, x squared. It's going to be equal to g, this force, ms divided by the distance between these two. Because the particle is on the same orbit, the distance is going to be r. So r squared. We can find r, j, and also s from that table. But g and m is going to cancel out from both sides of this equation. And we can find x, the distance between the particle and Jupiter, from this equation. X is going to be equal to r times the square root of mj divided by ms. And if you look at the table, r is 778 times 10 to the 6 meter, kilometer, times square root of mass of Jupiter is 317.8 times the mass of the Earth. If I show the mass of the Earth with ME, I have this for Jupiter. And also mass of the Sun, based on that table, it is 333,000 times mass of the Earth. Mass of the Earth is going to cancel out from numerator, denominator, and we can find x from this equation. So x is going to be equal to 24 million kilometer. So 24 times 10 to the 6 kilometer. So this is this distance, and we want to find theta. There are different ways to find this theta. Probably the simplest way is we can say this angle is a very small number. And if an angle is a small number, then the distance between the particle and Jupiter is going to be equal to the length of that arc. They're going to be very close to each other. And from the other side, the relationship between the length of the arc, the radius, and angle in radian, the length of the arc is going to be r times theta. Okay, so we can say x is equal to r times theta if you say theta is in radian. Then from here, theta is going to be equal to x divided by r. And if you multiply to 180 divided by pi, you can find it in degree. And if you just put the numbers, x is this and r is 778 times 10 to the 6, then theta is going to be equal to 1.77 degree. Okay, that's one way to find it. The other way, if you don't trust me and say we don't know the length of the arc is equal to the distance between M and MJ, we can say if you look at this triangle, these two sides are equal to each other, right? So if I draw a perpendicular line from the sun to this line, from here to here is going to be x divided by 2, right? So this angle, which is half of theta, sine of it is going to be x divided by 2 divided by r. So let's write it here. Sine of theta divided by 2 is equal to half of x divided by r. And if you put the numbers and do the sine inverse, you're going to find the same angle. It's going to be 1.77 degree.